Welcome to Brunda Engineering Academy. Today we will continue the concept of simple stresses and strains. Stresses and strains. Previously we have done one video. The continuation part is this one. If you missed that video, please watch that and continue to this video. Then now coming to the today's topic, that is for varying cross section. For varying cross section. Varying cross section. That means the area will be varies. So for example, I'm considering a bar, a circular bar. Its diameter is taken as d1, its length is taken as l1. Next, I'm reducing the another diameter here. Its diameter is d2, its length is taken as l2. Next, another one is there here. Its diameter is taken as its diameter is taken as d3, its length is l3. In this way we have. So then how can you calculate the stress and strains? Okay, so basically we know the relation. What is Young's modulus? Young's modulus is the ratio between stress and strain. Stress and strain. So our target is we have to calculate the strain. Strain can be written as stress by Young's modulus. Stress by Young's modulus. So here this can be written as what is sigma? What is sigma? Sigma means stress by strain. So P by A. P by A by E. P by A by E. Then it can be written as P by A E. P by A E. So then from that we can write strain equal to P by AE. P by AE. So strain is nothing but change in length by original length. So then P by AE. From that we can write the change in length equal to PL by AE. So in this way we can calculate the how much change is there by applying the tensile load or compressive load. DL change in length can be calculated by PL by AE. It is the basic relation. DL equal to PL by AE for a single component. Whereas for the varying diameters, various diameters are there. L1, L2, L3 lengths are there. So D1, D2, D3 diameters are there. So for that purpose, for that cases, we can calculate the total change in length. The total change in length DL equal to actually what is the for this we can get for the first component. It is the first component. It is the second component. It is the third component. So what is the change in length? DL1 equal to PL1 by A E. PL1 by A E. A1 E. Next here DL2 equal to PL2 by A2 E. Next in the similar way DL3 equal to PL3 by A3 E. PL3 by A3 E. So for the total change we can calculate DL1 plus DL2 plus DL3. Okay, then we can write PL1 by A1 A1E plus PL2 by A2 E plus PL3 by A3 E. Okay, A3E. So by the simplification, that means P by E is the common term. Then we can write it as L1 by A1 plus L2 by A2 plus L3 by A3. So here the total change in length can be calculated with this relation but the condition is the load is constant. Load is constant throughout the section, and Young's modulus is the constant. Then only, that means the total component is made up of a single material. Total total component will be made up of a single material. Suppose it may be steel, it may be the copper, single material. Why? Because if you change that material, type of material, then Young's modulus will be changes. Okay, so if the load is same, suppose if you apply the load P, common load, and here applying the load of P, then only it can be applicable. Otherwise, the condition is also there. If the material may be changes, that means different material may be considered, and different area is considered, area of cross section is also there, then how can you calculate? How can you calculate that analysis, analyze this section? So for that purpose, we can take the same relation that can be taken as dl equal to P by dl equal to, here P is the common term out of this P, then take this, here P into L1 by A1 E1 plus L2 by A2 E2 plus L3 by A3 E3. That means if the diameters are diameter varies and length varies and material Young's modulus varies. Okay, so then we should use this relation. You should use this relation for varying cross sections. Okay, so this is about the stress and strain analysis of the varying cross sections. Next, one important notation is there, that is the principle of superposition. Principle of superposition. Let us discuss about the topic. Principle of superposition. Superposition. Principle of superposition tell that the total, here we are taking dl equal to L1 dl1 plus dl2 plus dl3. While applying the load, the total change in length is the sum of the individual changes in length. Principle of superposition means the total change in length will be equal to the sum of the individual changes in the individual sections. So dl equal to dl1 plus dl2 plus dl3. Otherwise, it can be written as the total strain can be is the sum of the individual strains in the individual sections. Suppose E1 is the strain in the first section, E2 is the strain in the second section, E3 is the strain in the third section. Next, that is the principle of superposition. Next, one important point is here stress within elastic limit. Stress within elastic limit. Stress within elastic limit. Elastic limit is safe stress. Is safe stress. Important bit here. Stress within the elastic limit is the safe stress. Okay, that is one important parameter we consider. Next, suppose one circular rod is there. That circular rod is having taper section. Suppose it is a circular rod. It is having the diameter like this, and it is having the diameter in this way. Okay, its diameter is D1, its diameter is D1, its diameter is D2. Okay, how can you calculate the change in its length? Suppose if you apply the load P at the both sides, tensile load you may apply or compressive load you may apply. So for this type of cases, for the tapering, circular rod, tapering circular rod. For these cases, the change in length, DL is given by 4PL by 4PL by pi D1 into T2 into E. 4PL by pi D1 into D2 into E. P means load you have applied, and L is the length of the taper rod. Okay, L is the length of the taper rod. D1 and D2 are the diameters. Okay, initial diameter and here end point diameter. That means it is the tapering part. So it is the change in length for tapering circular rod. If the diameters are the different, okay. Whereas if the diameters are the uniform rod, that means uniform. That means if the diameters are the same, then DL equal to 4PL by pi d square E. Pi d square E. That is nothing but our regular thing, that is PL by A E. PL by AE, because 4 by pi d square. 4 by pi d square is nothing but the area. Okay. So here for the important concept in the ECET and gate point of view, the change in length for the tapering circular rod is given by DL equal to 4PL by pi D1 D2 into E. Okay. Next, here another concept, that is uniformly tapering rectangular bar. Uniformly tapering rectangular bar. Rectangular bar. Generally, rectangular bar means here the suppose in this way we maintain. Here it is a rectangular bar by the projection. Then uniformly tapering. Okay, tapering means here the same thing I am applying, but here not a circular. It is the rectangular tapering bar. So for that cases, the change in length DL equal to PL by ET into A minus B. A minus B into log E A by B, log A by B to the base E. So for the rectangular tapering bar, we can take it as PL by ET into E is the Young's modulus and T is the tapering. A and B are the dimensions of the rectangular bar. Okay, dimensions of the rectangular bar. Next, coming to composite sections. Composite sections. Composite sections means here it is one bar and another one is, this is another section. These two are, it is the total component. It is made up of the steel. And it is made up of the copper. Okay, that means these are the two different materials. These are the two different materials. That means it is the combination of the different materials. So it is the composite section. For that type of composite sections, how can you calculate? That is total load. The total load P equal to P1 plus P2. P1 plus P2. That means here we are considering. Then for this, we can take it as P1 means sigma 1 A1, why? Because sigma equal to stress equal to P by area. So we can write it as P equal to sigma into A. So for that purpose, sigma 1 A1 plus sigma 2 A2. Sigma 2 A2 we can take. So here the total load is in this way. Okay. So next, another concept, that is thermal stresses. Thermal stress. Thermal stresses. So thermal stresses means here a new concept is there, that is coefficient of thermal expansion, alpha. Coefficient of thermal expansion. Coefficient of thermal expansion. Coefficient of thermal expansion. Here, if the temperature of the bar, suppose I am considering a circular shaft or any bar, if the temperature is increases, then the length may be varies, the length will be changes. So for that purpose, here the change in length by original length will be given by alpha into T. Alpha into T. T is the temperature. So then the change in length is given by dl equal to alpha into T into L. Okay, alpha into T into L. Alpha is nothing but the coefficient of thermal expansion. That coefficient of thermal expansion is calculated by this relation also, dl by L into temperature. That is nothing but alpha equal to E into T. That means strain into temperature. Strain into temperature is the coefficient of thermal expansion. Coefficient of thermal expansion. Okay. So here, how can you calculate the sigma? What is the relation between stress and strain for the thermal stresses? So you know Young's modulus equal to stress by strain. So the stress equal to strain into Young's modulus. What is the strain? dl by L means alpha T into E. So the total stress equal to alpha into T into E. E is the Young's modulus. Stress can be calculated with the coefficient of thermal expansion into temperature into Young's modulus E. So here, for the competitive examination point of view, thermal stress means to know the thermal stress, we have to identify the coefficient of thermal expansion. Okay, coefficient of thermal expansion. Change in length by original length equal to alpha into T. So then here alpha equal to coefficient of thermal expansion equal to strain into temperature. Young's modulus is the ratio of stress and strain. So from that relation, we can calculate stress equal to alpha into T into E. And one important concept in the thermal stresses in composite bars. Thermal stresses in composite bars. The noted point is two bars are if two bars are different lengths. If two bars are different lengths, then deformation is same. Two bars are different lengths, then deformation is same. Okay. Next deformation. Next two bars are same length. Then strain is same. Observe the two different. If two bars are different lengths for the thermal stresses in composite bars. Thermal stress in composite bars. If the two bars are different lengths, then deformation is the same. Deformation means a change in length is the same. Whereas two bars are the same length, then strain is same. Next, another point is elongation. Elongation is nothing but a change in length. Elongation of bar due to self weight. Due to its self weight. Okay, elongation of bar due to its self weight. Suppose in this way In this way, one rod is there. So here this rod is hanged there. It is having the weight of W. Okay. So now what actual length is L. After some time or after applying, after some time the length may be changes. So for that purpose, the change in length DL equal to capital WL by 2E. Important relation. Change in length for elongation of bar due to self weight, that is DL equal to WL by 2E. Okay, in some cases they may be asked like this: W, small w, L square by 2 times of the Young's modulus. 2 times of the Young's modulus. Why? Because that is self weight equal to self specific weight into length of the bar. Specific weight into length of the bar. So it can be replaced with. So these two relations are very important in examination point of view. Change in length due to self weight WL by 2E, capital W, whereas small w means DL equal to small w L square by 2E. Here it is the specific weight, it is the weight of the body, weight of the body. Next, another is analysis of bar of uniform strength. Bar of uniform strength. Uniform strength. That means the strength is uniform throughout the section. Throughout the section. Then their ratio is A1 by A2 equal to E power WL by sigma. A1 by A2 equal to E power WL by sigma. It is for the analysis of the bar of uniform strength. So these are the different concepts involved in the entire stresses and strains. Okay, in the next video, we will solve the different problems asked in the previous examinations. If you like this video, please share to your friends and subscribe our Brunda Engineering Academy channel. Thank you.